Uh, to begin, I think for me is the Adirondacks, and I'm camper number 12110. Was here between 74 and 76, and I could never get in the big show, this big event they have at the end of the year, so I'm very pleased to actually be finally on stage at Witherby. Look at what I had to do. Yeah, this is the way I think about it. 30 years later is what it took, 30 years of all of this. But I would say there's something about the Adirondacks that's in your bones, and I would say that for me, it's a great honor to be, let's say, to be allowed to design such a bridge. Yeah? And what I would like to talk about today is really the evolution of the project, but really beginning with the existing bridge and just how important a structure I see that to bridge engineering. And I don't say that lightly. There are only a few important bridges, I would say, maybe 24 in the United States, and this was clearly one of them for some unusual reasons, at least from my perspective. And I want to talk about not only that, but also the difficult decision of having to close the bridge, which I was certainly a part of. And I want to get into a little bit of why that, in my view, it was so risky, the bridge. And then I'll walk you through the design, but also with some background to what I see as maybe the important pieces of what influenced the design for me as an engineer. In terms of the project itself as a bridge project with historical importance, when we were originally hired to do the job to design or rehabilitate the bridge, it was very clearly that decision. Should we rehabilitate or should we replace? And I have to say that my heart was on a rehabilitation strategy, mostly because of how important the bridge was in terms of its visual impact to the surrounding area. It's a bridge that's very visible because of its navigational clearance. You can see it for many miles. And lake bridges are very unusual in the United States and actually quite unusual in the world. So a lake bridge, which has so many viewpoints, has got so much vertical clearance so you can see it for miles. This is an important bridge visually. But the structural form was incredibly unusual, and it was an early moment in structural engineering. And this early moment was by a bridge engineer, Charles Spofford, who started a firm, FST. He was based out of Massachusetts, and he was an MIT professor at the time. Now, the story about Charles Spofford, which is very interesting and important in this story, is that he developed a way to analyze bridges. Yeah? This was the beginning of actually designing bridges by calculation. And so he developed a whole calculation method, and what it allowed him to do, once he understood how to design, he changed the form of what trusses are. And so if you look at, these are, on the left side is two of Spofford's bridges in Cape Cod over the Cape Cod Canal, built a few years later. This bridge is the Newark Bay Bridge, a bridge designed by my firm in the 1960s, yeah? And you can clearly see the closeness, yeah, that we as engineers are borrowing from the past, yeah, but also innovating a little bit. But what Spofford did is he took this form. This is the Tappan Zee Bridge. In my view, there's literally hundreds of those bridges that look exactly like that, where it looks like a suspension cable. The top chord follows the moment diagram, as they say. But that style, in my view, is very rigid. And what Spofford did in the beginning, okay, this was only the third highway truss bridge of its kind in 1929, was Spofford said you could play with the form, change the shape. Now, changing the shape sounds simple nowadays with computers and so on to analyze. It was hardly simple at the time, and some considered it a great risk. Now, there were some unfortunate problems with the bridge as we were just getting involved in 2009. And the most unfortunate part of the bridge was its substructure, its piers in the water. And for me, this represented an unusual aspect of design because you expect a truss that's 80 years old, you expect that to be corroded and potentially dangerous. And in fact, when we went out there, the piers were what really concerned us. The piers looked problematic. And there were a few decisions that Spofford made that were, I would say, not atypical of design at that time, but probably led to the bridge's demise. One was that he saw a pile of iron ore tailings, and took a look at the iron ore tailings and said, this is really good stuff, This would probably make some really good concrete. And being an MIT professor, he took the aggregate and made concrete and tested it at MIT, and he also tested it underwater. He was concerned about, these are very deep caissons, somewhere in the neighborhood of 100 feet. And the concrete was so high quality that he decided, and there's not much written about it, but he decided that the concrete didn't need reinforcement, And that was fairly unusual. The other decision that I think contributed to the demise of the piers was a decision not to use granite armoring, And this is typically what we use in river, especially rivers that ice. We'll use granite armoring to protect the concrete from abrasion. And the sense was that in a lake, lakes don't essentially have ice that flows, even though all of these lakes, Lake George, Lake Champlain, just because of the thermal cycle of the lake, you do get flows when the ice breaks up. But you tend not to have this problem with lake ice that you do with river ice. So even though another one of his bridges used granite piers, this General Sullivan Bridge, it was his decision, and he was asked questions about it. Why no granite? Why no armoring? And his decision, he's on the record for saying it's lake ice and it's not so much of a problem. Well, 80 years later, there was really some substantial damage right at the waterline, and that damage it roughly appears maybe 10 feet in thickness. I would say 18 inches along the girdle, along the bridge pier at waterline, was so damaged that it was rubble in your hands. So recognizing that the piers were unreinforced and recognizing that we'd lost maybe a third of the section, we got concerned enough to evaluate the safety of the piers and to do some tests. And initially, we took some concrete cores. Now, cores of the bridge, the piers had been repaired about 8 times over the life of the structure. In fact, they were repaired in 1945, which is highly unusual, to have a bridge that's only 15 years old that already need pier repairs. So my sense is there were problems a bit from the beginning, which is not unusual. But when we took cores, we really got more and more concerned. The first core we took out of the pier we were most concerned with, the old Pier 5, we found, when we extracted the core came out in pieces, and we found cracks deep into the pier, feet into the pier. So not only did you have this rubbleized area around the perimeter, but deep inside the bridge piers, we found cracks. And then we did what are called petrographic analyses, and this white stuff is called Ettringite, and this is delayed Ettringite formation. What happens is you get crystals that form in cracks that are pre-existing. Now, the problem with this is the cracks are happening right between the cement paste and the aggregate. And so part of the weakness of this concrete is really a function of somehow that aggregate cement paste interlock was damaged. We don't know exactly how. I still have a chunk of the pier that sometime we'll do some more forensics on. But we were moving too quickly to get really into a research project about what exactly happened. The only other thing that I would say is this is just before the period where we realized air entrainment was good for freeze-thaw behavior in concrete. That was started in the 1930s. Now we typically have air bubbles in concrete to protect it from freeze-thaw. So this was just 2 or 3 years before that technology was even understood. So then every freeze-thaw cycle added more damage, and there was clearly some significant damage. The bridge was already subjected to some pretty significant damage. Now, another area that I'm very interested in is bridge failures. And so there are a couple of failures nearby that are worthy of note. The Schoharie Creek bridge failure in the late 80s was associated with scour, that you had a high flow in the river, it undermined the foundations, and then you had an abrupt collapse. What's not appreciated about this failure is the abrupt collapse started here. You can see that there was a column right over here. That abrupt failure happened because this strengthened area was not adequately reinforced. And in fact, unreinforced concrete has this problem where, especially large-sized unreinforced concrete members, is you can generate a fracture mechanism and the failure can be abrupt. And that's exactly what we were concerned about here. No warning, yeah? A scour event, typically, if you had reinforced piers, you'd get some tilting, some signs of distress, not boom. On Schoharie Creek, you had really a very significant collapse. Now, there's a few French Canadians in the room, I'm sure, and this might be something that you would have read about if you were north of the border. This was a bridge that on one fine day in September, for absolutely no reason, looks like my microphone's coming. Davo with my microphone.
Two guys from the audio.
What's interesting about this one sunshiny day, for no reason, total collapse of an overpass structure. And both of these, by the way, a number of people were killed, both Schoharie Creek and this bridge. Now, this kind of thing shouldn't happen. Failures for absolutely no reason. Here again, this was large, unreinforced concrete. It had some reinforcement, but in the wrong place, and the collapse happened like this. Now, this is the area just prior to the collapse, and a chunk of concrete had fallen, and that chunk of concrete was the only telltale sign that something was going on, and the fellow who was involved in maintaining the structure was driving back to the office to make a phone call and say, hey, we got to take a look at this. What I hate to say it is this part of the bridge was repaired 5 years before the collapse. Yeah? So this was just repaired. So this gives you maybe a sense that we don't exactly know all what we think we know, especially about unreinforced concrete. And then the forensics investigations were very clear. When you took a brand new beam and applied load to it, you got exactly the same cracking mechanism. You can see that piece looks like that piece. Yeah, does that make sense? So here you see something that's large and unreinforced. That was 40 foot long. That's about the same dimensions as this pier. Yeah? And this becomes, is that better? Yeah? Witherby and a microphone. Wow. This is my big show days. I never got this. So anyway, these become concerns, but also triggers for making some tough decisions. Now, New York State had lived through the Schoharie Creek collapse. We had done some evaluations, both with core samples, and then we got the idea that we should do, first of all, a dive inspection, and this was actually post-closure. On October 16th, we decided that we could not speak to the safety of the bridge. It was already closed to one lane of traffic because of steel repairs, and based on our evaluation to date, we could not speak for its safety. We were not concerned with imminent collapse, but we felt like we couldn't leave the bridge open to the public, and we engaged in some, what I call, essentially post-closure work to make some tough decisions about how might we rehabilitate the bridge in an emergency to get it. We were really trying to get it open before snow flies. When the as many of you know, when the Fort Ticonderoga ferry is out of service, this becomes a 100-mile detour. So we were in October, we were making some tough decisions about what could we do to get the bridge open and see if we could extend the tie service for a month or two and try to get the bridge back open by the time snow flies. So the first thing we did is a dive inspection. Those of you familiar with Champlain know the zebra mussel infestation is significant. It took a week to clear the piers from zebra mussel infestation just to be able to look at them. And once we laid our eyes on them with divers, the results were even more concerning. This is a stick rule, for those of you know. It's a 1/2 inch wide. You had 1/2 inch cracks, not only in localized areas, but all the way around the piers. Yeah? And it was at this point that Tom Hoffman, the district engineer, the district structural engineer, great guy, and he had the presence, by the way, to take the cores when the water level, he knew I was concerned about the piers, As soon as the lake water level was low enough, he got more concerned about how much damage there was at the water line and had the presence to take some cores, and the cores came back bad. That's really why we were aggressive about closing the bridge. But essentially, these cracks made it absolutely clear we had a major problem. We instrumented the bridge, so we were actually measuring the bridge. Now, this is supposed to be an expansion pier. We put an instrument that measures not only accelerations, but whether the pier tilts. This is exactly what you don't want to see. The bearing should be moving, the pier should not be moving, and this is the pier tracking with temperature. Temperature goes down, pier moves towards the river, towards the lake, center line of lake. Temperature goes up, it moves back towards shoreline, yeah? And it's moving back and forth an inch, yeah? And when we back calculated where it was likely moving, it was moving at the cracks below water, yeah? And so this was, we were focusing on Pier 5, we actually put instruments on Pier 6, and then the instruments played an important role because we decided at this point that the bridge would need some very serious rehabilitation, not just at one pier, but possibly 3 or 4 piers. And so the challenge associated with saving the bridge was getting to be monumental at this point. The other little problem is ice is coming, and those of you who ice fish the lake know that on a good year you'll get 2 feet of ice thickness. And this is really where we started. This is, by the way, none of this research was done at the time, but since then I was invited to present some ideas about loads we don't design for, and I got very interested in lake ice, and we did some research to show that lake ice was very likely the culprit that caused the damage in the first place. But what I was worried about at the time was that if the expansion bearing is not moving and the ice is holding the pier in position, that you would essentially, the ice would be a pivot point, a fulcrum for the pier to get worse damage. And so the idea that we're headed towards winter, we have a complicated pier retrofit to try to pull off, and that ice might be part of the problem. It might be the worst problem we have, made us even more concerned. And then you can see the sort of damage that the piers were really in tough shape. So how would you say, signing on to their health, even in an intermediate way without major rehabilitation, was a challenge. So a little digression about lake ice. There's almost no research that's been done at all on icing, even though ice and lake ice has damaged bridges throughout the United States. This is actually a bridge in South Dakota that had maybe $2 million worth of repair associated with an icing event. And the ice thicknesses are round about a foot to 2 feet, not dissimilar than what we get here in a good year. Now, the other thing that I got very interested is this ridge of ice that forms when lake ice essentially acts like plates, tectonic plates, and you get a little lake-induced, a thermal-induced earthquake, yeah? And this was very interesting because the Japanese are fascinated by this behavior. But what happens is the ice gets restrained between shoreline, and when and this you can imagine happens quite often in Lake Champlain, you get a cold spell, deep ice, and then it warms up very quickly. Well, the ice wants to expand, the shoreline holds it in, and when it expands, it actually buckles, yeah? And so that buckling is what creates this sort of shape. Sometimes it happens at shoreline, often it happens in the middle of the lake, and Champlain is actually known for pressure ridges, not often, but in some cases severe. Now, this is a classic problem in Minnesota, is that the ice actually shoves up along the shoreline and does quite a bit of shoreline damage, sometimes taking out homes. So homes are set back from the shoreline, not because of zoning, because the ice has hit them before, yeah? And piles of ice are not unusual in Minnesota lakes. And so one of the interesting characteristics of Lake Champlain is that we have these almost mud flats near the bridge, and those are very unlikely to have the ice, if you will, ride up the shoreline. They'll really attach to the shores, and I'm afraid we get this sort of behavior, this ice pressure ridge. Well, the Japanese, of all people, have been not only paying attention to this behavior, but they have a name for it, Omiwatari, which is pathway of the gods. Their sense was that every time you had an event like this, the gods were trying to cross the lake. Yeah? And so once this happened, you'd have a big festival. And this is now nothing like a few thousand years of history. Since the 1400s, they have very accurate records of this Omiwatari happening on this Lake Suwa. Suwako is Lake Suwa. And so this is how we know most of what we know about global warming is from data like this, where we've got written history of an event that shows icing in a lake. Yeah? So we can correlate temperatures to a certain behavior and change in temperatures to a certain behavior. And so there's been a bunch of work by the Canadians and even some work on bridge piers, but mostly for river icing. And this strategy of having a sloped surface where the ice can ride up and break off is a strategy that the shoreline does nicely, and it's a strategy that we've at times copied for piers and we adopted here. But the idea that you can calculate the force associated with lake ice, this is I have to, because I'm an engineer, I have to show a graph somewhere with stuff that doesn't mean anything to anybody. This line is, if we know what we're doing, all the dots should be on this line, okay? Now, this is the Swedish, the Japanese, the Canadians, and us. We have no idea about how much load ice, especially lake ice, puts on bridges. So we ought to be conservative. Now, I have to say that nobody even designs bridges for lake ice. Yeah? So these are things we've missed. Yeah? And so in all of this, with ice coming and rehabilitation getting much, much more complicated, we had to make the decision to replace the bridge. Now, that represented its own major challenge because we had to decide, was there another location where we could put the bridge? And I can tell you at public meetings, that answer was loud and clear, yeah? So we didn't have to have a lot of meetings to discuss that. Yeah, that was I think that took about 3 seconds in the first public meeting we had on alternate alignments. So the bigger challenge becomes, how do you build a bridge on the same alignment with ice coming? The big danger is that if we were to drop the bridge, if the bridge were to fail on the alignment, that it would be a monumental effort to clear the bridge. Yeah? And so then we got into the mode of we need to demolish the bridge in such a way that it's easy to remove. Now, what was the challenge? The challenge is there's about 60 to 80 feet of soft mud. So soft that if you drop a piece of steel in it, or in the case of, we have these barges that have spud piles that you drop in to support the barge. The contractor was out there the first day with a 90-foot spud, and he lost it. Yeah, the spud just, now, soil should be at 30 feet, yeah? So that means you have 60 feet plus of soil that's so soft it can't support the weight of the pile itself. The barge wasn't on it, just the weight of the pile, just dropped into nothingness. Well, if you imagine the bridge dropping into nothingness, retrieving the bridge, trying to get the bridge out of the way, because we have to put foundations along the same alignment, is a disaster, yeah? And probably would have cost the project in the tens of millions and would have meant months, if not a year, to the schedule. So now demolition became really a focus of our work, as well as putting together a contract for an emergency ferry, which I'll get into in a second. But the demolition was scheduled for the 23rd. We missed it, and it was demolished on the 28th. It was absolutely, I have a nice video, but I won't play it. I have some other videos. It was, if those of you who were at the event, it was almost a non-event unless you're right next to the bridge because it was snowing so badly. Yeah, so it was really a rough day. These are about the best photographs that we had of the demolition. And the idea was to break the bridge. The reason you see all of these lights is the explosives were placed so that we break the bridge up into small pieces to make it easier to retrieve from the mud. Yeah? And even so, we had a few pieces that we didn't fully retrieve. One of the strategies we use in the Mississippi River is we tie flotation around the bridge and then pick it out of the water afterwards. But with the ice here, that was really would have been its own challenge, yeah, because ice had already formed by December 28th when we demolished the bridge. Now, obviously, the economic impacts for the bridge being out were tremendous. We were obliged to get a ferry system in place as fast as we could. The agreement on the environmental of the resource agencies, once you declare, both states declared states of emergency. Once you declare states of emergency, you throw the rule book out. I would tell you that we still followed on the ferry side most of the rules. On the bridge side, we followed all of the rules, and I really second, in my introduction, it was stated how both states work together, and it's not just both states, it's really both states, federal agencies, the Coast Guard, the Army Corps of Engineers, folks that don't necessarily work together that much, they really all came to the table. But essentially, we were in construction immediately with a ferry system, okay, a temporary ferry system, and that construction happened through the design of the bridge, and we were doing these things simultaneously. In terms of the environmental process, there's a public involvement component, and there was a steering committee, a public advisory committee that was very much involved in the concept development, and I want to walk you through that a little bit because it certainly influenced the design, but the public involvement was incredible. I've designed a lot of bridges all over the United States. I've never, not even close, had this sort of public interest in the project nor involvement. Yeah, it's absolutely unprecedented. Yeah, and I'll get to a little bit why. But essentially, we had a 6-day it was a week timeline. Now, to give you a sense, we were hired to do this. This was supposed to be our job, was to get through the type selection. It was a 5-year project that was around about $4 million in engineering costs, not money, not spending, building anything. Yeah, that's how involved the process typically is, and that's how long it typically takes. Yeah, 4 to 5 years and millions of dollars. Yeah, we did this in a week, okay? So you can imagine that we worked really hard, but we also saved a lot of money, and we had a lot of alignment in terms of folks coming out to participate in what the design would be. And this was in the middle of December, and we had meetings, for those of you, and a few of you are here from those public meetings. The meetings were in Ticonderoga, and it wasn't easy to get